Okay. Perfect. Okay.
So
Good morning to most of you here in Europe, and the ones who are joining from India, good afternoon. And thank you for being part of this training. As you know, in the first webinar, we have already explained to you how this whole training will run. And Carlos is going to be coordinating, and Venkatesh from India will be actually delivering this whole. Vijay, can you mute yourself?
Sorry, ma'am. One sec. Yeah.
So, yeah, so Venkatesh will be delivering this whole training along with a few members of his team, and also my student Suman will also be part of this training. So just to let you know, I'm also from Europe. I'm based in Ireland, and I work in Tyndall National Institute in Ireland. And we specifically from Tyndall, the team would be happy to help the registrants of Europe to handhold you all a little more closely than we would do for the rest of the world. So do not feel shy to approach Venkatesh or me for any technical doubts. Venkatesh and me are from the MEMS background, and we are there to help you all understand this technology, enjoy the learning. Don't take it very stressful. It's not very difficult to start with. It might sound very difficult, but it is actually not difficult. I always say this: if I can do and get well versed with MEMS, anybody in this world can. So it's not very difficult. It just requires a little patience from you in the beginning, because it is a little cross discipline from electrical engineering and mechanical engineering. And to get certain concepts right, if you're from electrical engineering, to get certain concepts right from elements of mechanical engineering, like what is stress, what is strain, what do you mean by deformation, what do you mean by displacement, the Hooke's law, all these things can be very strange in the beginning, even though we have learned it. At least I've learned it decades ago. So when I got into MEMS, this was the most difficult part for me to understand the mechanical engineering concepts. I would go and ask very silly questions to my professors, asking them to explain what's the difference between deformation and displacement. For me, they looked and sounded very similar, that if there is a deformation, there is a displacement associated. So what is the real difference between these two? So it sounded very silly, but then if you go in deep, it is not so silly, because they are associated, but they are not the same. So what's the difference between stress and strain, and how they are interrelated to each other? On the other hand, if a mechanical engineer is here, would find the electrical engineering aspects very difficult. So Hooke's law is very common for mechanical engineering. For the electrical engineering people, Ohm's law is equally common. But you have to think that Ohm's law and Hooke's law are exactly complement to each other in many fashion, and they're both equally important in MEMS. So anyone who's coming from mechanical engineering would find the electrical engineering part a little difficult in the beginning, but it's all the basics. It's all finally fundamental physics and nothing beyond fundamental physics. So do not be scared to ask questions. You should ask questions. That I would encourage each one of you to ask the question, and only then you learn. And over this period, as I said, we will help you understand. We will handhold you. We will not leave you isolated. When the devices come to submission of designs, what we will be doing in the weeks to come is Venkatesh and Carlos, I can help them as well. We will divide you into smaller groups. And what we'll do in these groups are we will put few of y'all who understand MEMS a little beforehand. And we will have in the same group few people who understand MEMS and who are new to MEMS, and we'll make you as one group. We'll allow you to interact. We'll allow you to decide what kind of design you want to submit, and then help you as a group submission next year. So next year from January to May is your time to design, simulate, and submit a design for fabrication. So that's between January to May. And then in the month of from June and July is a lot of work for me and my core group here. We will run your designs through what we call a design rule check, which is from the foundry. And once it passes those design rule check, if it doesn't pass, we will definitely come back to y'all and tell you all to make what corrections need to be made, and then take the final designs for fabrication in the July run of the Science Foundry. And once it'll take a couple of months for them to fabricate it. Once the designs, devices get fabricated, you will get your devices back for testing. I can't give each individual a device to test. So it'll come in certain areas and we will inform you. We will see, depending on how many designs get submitted, we will, our idea is to fabricate every good design that gets submitted. We will not leave any device that is fabricatable unfabricated. And then comes the aspect of testing. Since, as I said, I'm based in Europe, I will make sure that all the devices of all you people get tested in some place. Tyndall have some testing capabilities ourselves. We could do some here. What we don't have here, we will get it tested elsewhere. So I'm there to help y'all. I'm there to help the coordinators. I'm really thankful to Venkatesh and Carlos for coming forward and being part of this, and all to you for registering. And welcome again. And I stop here and let Carlos and Venkatesh take it forward. But as I said, feel free to contact me or any one of these people, and we are there to help. And welcome on board and have fun while you learn. Carlos, Venkatesh, you can take it from here.
Thank you, Eda. So can you hear me?
Yeah. Yes, Carlos, we can hear you.
Yeah.
Okay, so thank you for the introduction. So we will follow with the session. I will give the word to Professor Venkatesh to begin with the training.
Yeah, just before Venkatesh starts, I want to say the next webinar by me will be on 29th of this month, October, and it will be from 3 to 4 p.m. Irish time. And Central CET time, it is 4 to 5 because you're 1 hour ahead. And just for the Indian crowd who is here, it will be from your 8:30 p.m. to 9:30 p.m. It is 1 hour later than the first webinar for the Indian people, because in Europe, the winter time starts and we'll be 5.5, I am 5.5 hours behind the Indian time, and Central European time is 4.5 hours behind. So that webinar will be on understanding the concept of what is MPW, the meaning and the concept of it, and also from the director of the foundry where this will be fabricated, that Science Foundry. So I stop here and I will leave in some time. Venkatesh, please take it over.
Yeah, thank you, Veda and Carlos, for the introduction. And let's get started. Myself, Venkatesh from BITS Pilani campus. And in this course, basically we will look into, as Veda has already told you, towards the end of this, we should be able to send it out for the fabrication. And in this, we will take you run through a journey on, we'll start from what is MEMS, or what the materials we need to select for MEMS. Then we will go forward for the design, followed by the different ways how we can simulate your designs and come out with your final design out, and followed by the different fabrication process which are available, and where you can characterize your devices. We will cover the entire journey from the what is MEMS to how we can characterize the devices. So in the today's session, I'll just start with what is MEMS. We should start from what is MEMS and website, right? So hope my screen is visible, right? So
Yes,
myself Venkatesh from the BITS Pilani campus, And this is a joint program between IEEE and IEEE Sensors. So okay, sorry for the inconvenience. And myself Venkatesh from the biomedical. You can always write to me. This is my mail ID over here. You can either write to me or you can write to Veda, or you can even write to Carlos as well, right? And you can even write to Suman, and Pradeep is also over here. We are always there to help you out. We will never assume that you know anything and everything, right? So even anybody in that matter, whether you are 20 years in this journey or you are beginner, so there is always things to learn, right? So we will start with what is done. So in this, we will start with the goal is to basically learn the basics of the MEMS, and then to address as there's a multiple disciplines are there, so you may be electrical engineer or you may be a mechanical engineer. Some people may be a chemical engineers as well. So the MEMS is not restricted to one journey and one branch under consideration. MEMS is a completely interdisciplinary under consideration. So whenever to pick up a MEMS, whenever let's say that you have some intuition in your mind, right? So what are the different things which comes up? The one first and the fundamental thing is the design of any object under consideration. Let us see that I wanted to design this, right? So first is that I need to look into the safety of it. So first and the fundamental thing, what comes out will be the design of an object. And then let's say that you want to design anything. Then next comes up is that let's say I want to machine it. Let's say in the conventional foundries, we will say that let's say I wanted to machine this component, then later you will go to your lathe machine or milling machine and you want to do this, right? Similarly, in case of microfabrication, there are always the fabrication constraints which comes up to in the design itself. So we need to keep in mind the fabrication constraints during the design phase itself. So one need to understand what is the different fabrication process we are following for actually for fabricating our devices. So the devices can be of several designs, right? There can be plenty of devices depending upon what is the final application. You are going to design your device upon, right? So the MEMS can be either it could be a sensor or it could be an actuator under consideration. How can you get a feel of what is a sensor, right? So how can you get a feel of sensor? For example, you take up your skin. Our skin is a wonderful sensor, isn't it? You tweak your skin, what would happen? I would like it to be a more interactive. That could be better for both of us. If you tweak your skin, you will feel it, right? How do you feel it up whenever you tweak your skin? So whenever you tweak your skin, so there is actually a mechanical stimulus what is coming onto this, right? So which is a mechanical stimulus which further gets converted into a neurological output, right? So whatever is a mechanical input now get converted into a neurological output. So our skin is also, there are plenty of sensors are also there within our body. If you take up our ear also, within our ear, there's basically acoustic signals are coming in. Those acoustic signals are again getting converted in. Yes, Kavita, please.
MEMS वाली एक हो रही है इस टाइम पे क्लास यस मैम अभी मेल आई
Can you please mute yourself?
इस टाइम का नहीं पता था मैम इवनिंग का
Hello,
पता
Kavita. Can you please
Carlos,
mute
as
yourself?
an admin, Carlos, I think you can mute her.
1 से 3 मैम पहले नहीं आई क्या आई थी
Yeah,
मैम
I'm trying to mute, but I cannot.
Participants, please mute yourself unless you don't have any questions with you.
मिल क्या थी
Kavita, can you please mute yourself?
Right. So another example, what we can think of in case of a sensor would be that you take up your ear, right? If you take up an ear, we do have a eardrum, right? So whenever there are the acoustic signals are coming in, what would happen? There will be a vibration of our eardrum. The vibration of the eardrum further gets converted into the neurological output. So basically, the mechanical stimulus, what is coming in, gets converted into a neurological output, right? So there are several examples I can even give you regarding the sensors as well. And also, whenever you think of any of the transducer, let's say that if you take up any of the energy domain under consideration, let us say that I am going to take up an object and I am going to pick up an object, and what would happen if the object is at a different level from the ground? It's basically having some potential energy associated with it, right? And let us say that it's going to come to the ground with a different a desired velocity v, then it has a kinetic energy associated with it. So this potential energy and kinetic energy are basically the mechanical form of energy, right? And also, whenever you take up electrons are flowing within a wire. They're basically the electrons, if they are flowing, then it's basically my electrical form of energy. And whenever there's a chemical reaction takes place, then we do get chemical form of energy, right? And also, whenever you take up any reactions under consideration, then there will be a temperature which then what if the structure may get heated up, right? So there will be a thermal form of energy, and let's say take up the photons which are coming out, and it will be either photonic energy or in general my optical form of energy, right? So there are several forms of energy, so on and so forth. I can give several forms, right? So let me replicate the same thing over here: the mechanical form of energy, electrical form of energy, chemical form of energy, thermal form of energy, and the optical form of energy, so on and so forth, right? So let us say that whenever this is the one form of energy, energy form 1, this is my energy form 2, the conversion from one form of energy to the another form of energy is basically is what we call it as the transduction, right? And the element which does is basically what we call it as a transducer, right? So this is a transducer. The element which basically does the transduction is called a transducer. And these transducers can be classified into a sensor or an actuator. So as the name itself, it can be classified into two categories. One is a sensor, other one is an actuator. As the name itself says, sensor, what exactly is a sensor? Name itself says, here we have the term sense. That means what should be able to measure, right? So whatever is the one which gets converts all the form of energy to a measurable form of energy is basically what we call it as a sensor. So which is how easily we can measure it. One can easily measure the electrical form of energy. So one which converts all the form of energy to the electrical form of energy will basically call it as a sensor. On the other hand, if you take up the actuator, here you basically have the term actuate. The actuate basically means what? Motion, right? The motion is what form of energy? Motion is basically a mechanical form of energy. So one which converts all the form of energy to the mechanical form of energy is basically called an actuator. So one can classify the complete transducers into a sensor or an actuator depending upon whether it's going to convert into electrical form of energy, it's a measurable form of energy, or it's going to convert it to a mechanical form of energy. If it's a mechanical form of energy, then it's an actuator. If it's the electrical form of energy, then it is a sensor. Right? So in this course, we will learn all the key topics, starting all the way from the microsystem design to the fabrication, and then what are the Now, these are the two books which you can actually buy and learn from there. One is the Microsystem Design by Stephen D. Centuria. You can even buy it through Amazon. It is hardly around 1,000 rupees in Indian. And then one can even well refer to Professor Anand Suresh book, which is around 600 rupees on Amazon. And these are the other reference books which you can even follow. The one is by Mahalik Matmadov is a wonderful book for the fabrication. And even you can follow the Nadim Mar or Chiang Liu. And let's say that if you want to stay up to date in the as per the technology, you can always follow these journals in the JMEMS, JMM, micro nanofluidics, IEEE Sensors, PENAS, Science, Nature. Now let us see what is the basic motto for the MEMS. Right? We need to have some motivation for any technology for the development, right? So if you take up the industrial revolution under consideration, the first industrial revolution basically led to basically it was a transition to a new manufacturing era. Basically, the Europe and US are the one which moved from manual to the machine ones, which is basically from 1760s to 1840s, which basically led by chemical, iron, and the textile industry, and followed by the second industrial revolution, where there was a rapid standardization and industrialization from late 19th centuries to the early 20th century, and followed by the third one, wherein internet and energy and all IoT, everything played now pitched in the third industrial revolution, where the new financial system also came into picture. So as we know that in the IoT and other things, now the ongoing one is basically IoT, cyber physical system. So as we know that whenever you take up any of the IoTs or IIoTs, these sensors play a very, very critical role, right? And it's basically integration the plenty of sensors together, right? So one need to, so MEMS is a driving parameters for all of this. So whenever you take up a technology evolution under consideration, now this is what, so this is what you can see, whether you take up a textile industry, or you take up an automotive sector, or you take up a energy sector, or you take up a biomedical sector. So what it was yesterday, in the previous generation, whenever you go to a doctor, right, they used to take up what several months together to tell you what disease you had, right? Now what you have it today. Now, within the prick of your blood, within your time, you will get to know what is your blood pressure level, what's your blood sugar level, everything you will get to know, right? This is what is the present generation. So what you would expect tomorrow? Tomorrow would be something like this. In the automotive industry, you look into what it was earlier and what it is now, right? And tomorrow you will may get Apple cars, and within your smartphones also, you will get all the X-rays, everything will be within the palm. Everything you can get it on your palm, right? That's what you will get it out in the tomorrow's generation. So in the technology evolution, there are plenty of this. So as we can see that what is there yesterday, what is now, and what we would get tomorrow. So what is the basic thing difference between the previous generation, present day, and the next generation? So what is it is basically accuracy, cost, and time. It's basically a so the present generation, it's the accurate, cost effective, and time effective, right? So these three are the driving parameters: accuracy, cost, and time. So it's basically act. It's basically act now. So for the betterment of the tomorrow, right? So how can we act for it? So act in the R&D. It's accuracy, cost, and time. Act in R&D is basically accurate. It should be accurate enough, and it should be precise. For example, it could be a dengue detection, or it could be monitoring a fuel adulteration, and then it should be cost effective, right? One should be able to afford it, right? It could be an electronic gadget or be a biomedical device. In the previous era, what we used to do, we need to use to go to doctor and also For each and every checkup, we need to pay heck lot of money. Also, nowadays, now the mobile phones, cost of the individual mobile phones have come down quite drastically. Why is it so? This is because of semiconductor revolution, right? Yeah. And also, in the present day era, it's a ultra fast and advanced in diagnostics also, and it's a competitive also, right? So we need to see look into all three of them: accurate, cost effective, and also it should be time effective. That means it should be ultra fast and it should be quick, and it should also be accurate enough. So what is the one which could give us the act in the present R&D is the micro and nano systems. The micro and nano technology is proven to be an answer for this, right? So that's why your MEMS and NEMS plays a very, very critical role, which are accurate enough, which are cost effective, and it is also ultra fast. It is proven to be an answer for all three of them. So let us look into the micro and macro world. So let us take up all the way from atomic mass. Let us take up a single atom, which would be around few angstroms. On the other hand, for you to get a feel of what is a micron, you can take up your human hair, right? What would be the typical dimension of your human hair? Anyone, please? What would be the typical dimension of your human hair? It would
60
be
microns.
60 microns. Okay. Any other answers, please? Anyone else? Vijay said 60 micron. Anyone else wants to take up? Okay. Typically, if you take up a dimension of your human hair, the diameter of your human hair will be in few hundreds of micrometers under consideration. That will be the typical dimension of your human hair, right? So that's how you can actually get a feel of the what is it, what exactly is a micron under consideration. So on the other hand, if you take up the what your the single cell under consideration, single cell will be in tens of micrometers, right? That's the diameter of a single cell, and the human hair will be in few hundreds of micrometers, right? And the virus under consideration will be around few nanometers under consideration, right? And also, if you take up a humans, if you take up the size of our entire human under mass under consideration, it would be around few meters, right? Isn't it? And on the other hand, if you go to that for a Earth and galaxy, that will go to a macro scale objects under consideration. So, can you tell me whether it's a normal scale or a large scale? Is it a normal scale or a large scale? You can see the scale over here, right? Is it a normal scale or a large scale? Okay. And now you can even see that the different things. So all of you are playing with a tennis ball, right? The tennis ball will be typically around a few centimeters under consideration. On the other hand, our RBCs will be typically around few micrometers. That's the tens of micrometers. Whereas if you take up the X under consideration, they will be around 1 millimeters under consideration. And I already told you the virus will be in few hundreds of micrometers. On the other hand, the water molecule, if you take it up, that will be around 0.1 nanometers under consideration, right? So if you compare to the micro scale, as I told you for the how do you get a feel of the micron. So here you can see one set of micro scale objects. On this side, you can see the other set of micro scale objects. So what is the fundamental difference you can see between the two? You can even put it in the chat box, or if you want to speak, you can speak out, not an issue. Let it be interactive. What is the fundamental difference you can see between the left and right? Yes, please. What is the fundamental difference you can see between left and right?
Living organisms and mechanical systems.
Yes, precisely, right? These are basically the natural system and these are basically the man-made systems, right? Within the nature also, we do have plenty of micro and nano systems, right? On the other hand, if you take up the whatever we are going to make it up, even there also we do have plenty of the man-made systems under consideration. So this is basically the what you can see starting all the way from nano world to the micro world to the macro world. So whenever you take up the miniaturization under consideration, the miniaturized devices can range all the way from 1 nanometers to 1 millimeter under consideration. So from the top down approach basically came to your micro machining that led to the microsystem technology. All the microsystems under consideration typically in the range of 1 micrometers to 1 millimeter. On the other hand, from the bottom-up approach, which is inspired by the Richard Feynman's star, wherein which further led us to the development of your nanotechnology. The dimensions of all the nanoscale devices typically range from 0.1 nanometers to 0.1 micrometers in their consideration. Right? So now, what are the different benefits you could get out from the microscale objects under consideration? So whenever you come down to the micro scale, you would get better surface area to volume ratio. And since that the micro scale, they are quite quick, so one can even well use them in the automation as well. And since they are small in size and also small mass is also quite small, and then since they are small, mass is very small and the dimensions are very small and power consumption is also very small. We will go into the details of all of that. And since we are going for the batch production, so cost per product will come down drastically. That's why nowadays the cost of the entire mobile phones have come down quite drastically, right? On the other hand, if you would have purchased in the earlier days, then even for a small mobile, you used to pay heck lot. My initial mobile, the first mobile what I had purchased, which was somewhere around 20,000 or so. Now in a 20,000, you will get a wonderful smartphone, isn't it? So it's easy to integrate the micro and nanoscale devices, and one can even play also with these micro and nanoscale devices. They are a small thermal constant, and we will go into each one of them. Let us not so as to get a feel of it is a individual MEMS device, what you can see, and this is a coin. So the MEMS device is much smaller than a single coin under consideration. So whenever you go for a miniaturization, so the miniaturized objects, they move very quickly. They move very quickly, right? So one can even well have a rapid actuation also with the help of the miniaturized devices. And they indeed encounter a low thermal distortion and also less mechanical vibration associated with it. And then they are even well suited for the aerospace industry and also for the biomedical sector. That's where the entire area of the lab on chip and organ on chip do come into picture. And also, if you take up the aerospace industry, wherein now if you are seeing, even the ISRO has even well used the MEMS-based gyros for the navigation, right? So there are plenty of the MEMS-based sensors which are there in the aerospace industry, and also they do have a low thermal expansion coefficients, but also the space requirement is very less for the micro and nanoscale devices. And also, whenever you take up there is a less material requirement for the micro and nanoscale devices, and one can even well do the mass production. So I told you about the surface area to volume ratio, right? So if you take up the surface area of a sphere, which is basically a 4 pi r square, whereas the volume basically scales as 4 by 3 pi r, right? So if you take up surface area to volume ratio, which basically scales as 3 over r, I am basically dividing this by this, then this basically gives us 3 by r. So this surface area to volume ratio basically scales as the reciprocal of 1 reciprocal of this R, right? That's basically scale says R inverse. So if you take up R in length in the meters, then 1 by R will be 1. If you take up that in millimeters, it will be this. So as we can see, the surface area to volume ratio will go up. Sorry, this should be 1 micrometer, not millimeter. If it is once you go from macro scale to micro scale, the surface area to volume ratio will further go up, right? So what does that mean? The surface area to volume ratio increasing. If the surface area to volume ratio increases, what does that mean? That means the surface effects will overtake the volumetric effect. So what are the surface effects? What does the surface effects mean? So materials with high surface area to volume ratio uh, will have much faster rates. Why is it so? Now take up an example of a salt, right? If you take up a fine grounded salt, they dissolve quite quickly. Why is it so? Why does the fine grounded, you take up a rock salt and you take up a fine grounded salt? Which one will dissolve quickly? Whether the fine grounded one or the rock salt? Which one will dissolve quickly? Whether the fine grounded salt or the rock salt?
Fine
The
ground.
fine grounded, right? Fine grounded salt. Why is it so? Why is it so?
More surface
Because
area.
yes, precisely, right? We do get more surface area for the reaction. That's why the fine grounded salt will dissolve much quickly. On the other hand, we can even see that if you take up, right, the fine dust, right, fine dust, the fine grain dust will be much more explosive in contrast to the other one. So if it's just a grain, you won't get it won't be explosive. On the other hand, if they find dust, the consolidation, it will be explosive. Whenever, what does this MEMS basically stands for? MEMS basically stands for micro electro mechanical system. So micro is basically, it is micro fabricated structures. Micro basically stands for SI, and electro, it would be electrical signal input or electrical signal output. And mechanical, it has a mechanical functionality associated with it. One could be in the form of a simple cantilever, what has been shown here, or it could be with the help of a plate suspended with the help of set of beams. It has some mechanical functionality associated with it, and one can even well come out with the structures, devices, and the systems out of it. So one can even well have the controls associated with it. Either it could be a mechanical input, electrical output, or the electrical input, mechanical output. So MEMS will have both. As I told you earlier, transducers can be either a sensor or an actuator. If the electrical input, mechanical output, then it will become an actuator. On the other hand, if it's a mechanical input, electrical output, then it would become a case of your sensory applications. So what are the different features of your MEMS under consideration? So MEMS does has a electrical functionality, it does has a mechanical functionality, and in general, there is actually a marriage between the electrical and the mechanical physics, which comes in one case of a MEMS devices. It's not just the mechanical or not just the electrical. So there is actually a coupling between both of them, right? So there is a marriage between both of them. That's why one need to look into the complete electromechanical physics over there, right? So on the other hand, you might have already, some of you are already from the electrical background, you are already aware of the microelectronics. In case of microelectronics, there are no movable structures under consideration. Whereas if you take up a MEMS, we always have the movable structures associated with it. And the majority of the MEMS devices, we do even go forward for the microfabrication, for the fabricating the structures whose dimensions, as I told you, the individual component dimensions will be in the range of 1 to 100 micrometers, whereas the complete device, if you take it up, it will even go to few millimeters under consideration. Right? And they have a unique feature that they do have a large surface area to volume ratio. And there are plenty of applications. You can take up any application, you can see the MEMS and NEMS devices being there. whether it is an automotive industry, whether nowadays if you take up any of your cars, there are MEMS devices there, right? Whether it could be in the airbag deployment or could be in the suspensions and the automatic doors, there are MEMS devices there, right? And also even your within your mobile also there are MEMS devices, right? Even in the consumer electronics and as I told you, in case of biomedical devices, there are MEMS devices now. That's why the entire area of the biomems comes into picture. And also we are developing on the lab on chip, organ on chip, right? Nowadays we are developing the artificial organs and the entire, as I told you in the earlier slides, that nowadays we within the prick of your blood, we will get the entire report, everything out, right? And we can do the complete PCR on your chip itself, the polymerase chain reaction, entire thing you can do it on the chip. That's where the entire lab on chip comes into picture. And one can even well have the micro machine, the STM as well. That's also is possible, right? And also whenever you pick up the several industrial industry sectors, one can even well use it for the shock testing, even for earthquake testing. There are plenty of devices which basically make use of your MEMS chip. Not only in this, they do even use it in the sports industry as well. For example, they do make use of the wearable electronics of this, all the wearable electronics, so as to improve the performance of the sports person. They do make use of the wearable sensors, and by making use of the wearable sensors, the coach will get the real-time performance of an individual so that he can always train the individuals as per the requirement, right? So actually these devices are aiding the coaches for quite a lot of applications. And also in the commercial applications like your inkjet printers, accelerometers, and this is what you can see over here in case of inkjet printer. And there are plenty of applications, even the accelerometers, gyroscopes are also there, right? Now you can even well design these accelerometers and gyroscopes, pressure sensors. You can always even well develop it with the help of the science foundry as well, right? But in the science foundry, you can't develop the biomedical devices because in the biomedical devices, you would like to go with majority of the times with the PDMAs and the other things. But with the science foundry, we are sticking on to the silicon-based devices. So I would suggest you people to look into the silicon-based devices, right? So you can go with the accelerometers or with the gyroscopes, or you can even well design the electrothermal actuators, or you can even well design the micro machined micro mirrors. That is also is possible. And then switching displays are also possible. We can do that, right? And all of you are using the smartphones, isn't it? Within the smartphone, see how many MEMS-based devices are there. We do have a MEMS-based accelerometers, gyroscope. Look at this. Each and every place you can see the MEMS device over there, right? So the MEMS is almost everywhere. In the day-to-day life, you are using MEMS. So within your car, you have the airbag deployment, right? So which basically is consisting of the analog devices accelerometer, right? So if I open up this, it basically has the analog devices accelerometer over here. So on the other hand, one can even we have developed in our own lab at the BITS plan itself the viscometer under consideration. The viscometer basically measures the viscosity of any fluid under consideration. And this is what is developed at the Sandia National Laboratory, the gears and gear drive. The you might have measured the mechanical people have realized the gears and gear drives in the macro scale. The same thing you can even well realize at the micro scale as well. You can realize the gears and gear drives at the micro scale. And there are plenty of MEMS products under consideration. If I pick up the MEMS sensors, we can even well develop the acoustic sensors, even the biomedical sensors, chemical, optical, pressure sensors. You can even well develop the stress sensors, thermal sensors. As I told you, there's a fundamental difference between a sensor and an actuator. In case of actuators, the Professor Anand Suresh talk, he actually showed you the grippers, the micro machined grippers, if you remember it, right? In the webinar, the Professor Anand Suresh has showed you these micro machined grippers, which are used for holding the cells and then to manipulate the cells and see what exactly is the force which is applied by the cells onto the gripper, and you can even well apply the force onto the gripper and measure how much is the displacement of the cell. That's what you can even play with the MEMS on several devices under consideration. Even you can develop the grippers with the help of your science boundary. That is also is possible. Grippers and tweezers is possible. You can develop it with the help of the science boundary. And also, as we see, the MEMS devices or the microsystems under consideration is a combination of a sensor, actuator, and a signal transduction, right? It could be in the form of a micro machine accelerometer, like an accelerometer, gyroscopes, which are the inertial sensors, or it could be in the form of any of the microfluidic platforms as well. But these inertial sensors are typically made out of silicon or silicon family, silicon, polysilicon under consideration. On the other hand, the microfluidic these sensors are typically made out of the PDMS. Basically, most of the things will be made out of the soft elastomeric. It's not only the PDMS, there are several other soft elastomeric materials are there. So, in the earlier days, as I told you, the cost of an individual MEMS device used to be quite large, right? Now the cost per product has come down quite drastically because of the industrial revolution, right? Now this MEMS is almost everywhere, right? So MEMS market is there in, if you take up anything, you take it up, MEMS is almost there in each and every field, right? So what are there are several career opportunities for the MEMS. So some of you might be the budding researchers. So there are plenty of opportunities for the MEMS. Now due to the ISM is actually pouring money for the MEMS and NEMS industry, right? For the semiconductor industry, when one of it is MEMS and NEMS. As a design engineer also, we can explore as a software developer to tool developer also one can have, because majority of the MEMS softwares like the commenter ways or the internet suite, they are quite expensive. Or if you wish, you can even well develop your own software too. For example, with Professor Suresh and Professor RP, we had developed one of the software tools as well. I think Professor Suresh has showed you in one of his webinars in the previous webinar. I think Veda and others are already having that. And you can even well become a fabrication engineer. And yes, Suman, would you like to say something? I think Suman also is having the access to that software as well, right, Suman? Which Professor Suresh has developed. And you can even well come up in the academia as well. And if you look at it here, the MEMS devices are almost everywhere. And I would prefer you guys to go through this about the history of MEMS and all those things, because within this 2 hours, I can't cover each and everything. I would prefer you to go through these 3 links. I can pass on these 3. Please do go through that. And how do we proceed with MEMS? In case of MEMS, we basically have MEMS sensors, MEMS actuators, and the microelectronics. Sensors are basically the arms, eyes, and nose for your devices. They will constantly gather the data. And then what type of data? It could be mechanical data, thermal data, biological data, chemical data, optical, magnetic, and it will pass on to the microelectronics. And what will the microelectronic do? These are basically the brains for the MEMS. They play smartly with the data. They refuse the data, they process the data, and they take such the decision. And further, they will send it to the actuator. The actuator acts like a switch. They will trigger and activate the external device. They will make the decisions based on the data. And then this microelectronics will tell the micro actuator to activate that particular device. So this is basically the MEMS device completely on the code, which basically consists of a sensor, actuator, and a signal transduction system. And we are going to power up the entire signal transduction unit. And if you look at the different horizontal component of the MEMS device, in the previous one are the different vertical components. On the other hand, if you look at the different horizontal components, let's say that as I told you, if you have inclusion in your mind, we need to come out with some product. So these are the different components what you need to do. The first and the fundamental thing is the design and simulation, right? And Suman is going to take up one session on the how we can design the MEMS and NEMS devices in the console or any of the softwares, right? And also after the design, right? Let us say you have some inclusion, you have to first and the fundamental thing is that you have to come out with the design. Fine. For the design, one can do with the analytical formulation or with the numerical formulation. For the numerical things, you can either make use of console multiphysics, or you can even well use MATLAB, or you can even use the CATIA, or you can even well use the ANSYS, or you can make use of the MEMS-based tools like Coventerware, or you can make use of IntelliSource. There are plenty of MEMS-based tools are available as well. Or you can always make use of console multiphysics also. And after the design, let us say that if you are done with your design, the structure could be in the form of a MEMS-based inertial sensor, or it could be a microfluidic platform, right? So we need to keep in mind what is the final, and whenever you are designing, you need to keep in mind the fabrication constraint. So in the Veda has just told you that after you send out your design, we will always run the design rule checks, right? So you need to keep in mind the fabrication constraints in the design phase itself, right? So after the design, we should be able to fabricate your devices. So in the fabrication, there are several fabrication processes are available. So in this science boundary, we are basically going forward for the SOI MEMS process. Earlier it used to call the MEMS process, now it is called the science boundary. So you need to keep in mind what should be the structural layer thickness and what should be the gap you need to have. So everything should be kept in mind. So one can fabricate the devices by the bulk micromachining, or one can fabricate the devices by the surface micromachining process as well. So in this case, we are going forward by the science boundary. So whenever I discuss the fabrication, I will go into the details of the fabrication, right? And after you have fabricated your devices, next comes is the characterization under consideration, right? So we need to see whether your devices are up to the expectations or not. So as to do that, we need to characterize our devices. So the characterization can be done at wafer level characterization or at system level characterization, right? So what are the wafer level characterization? In the wafer level characterization, one can look at the electrical characterization, or you can look at it from the mechanical characterization, or you can look at it even from the chemical characterization. There are plenty of things are there as well, right? And also one can look at it from the system level characterization. I mean to say that, let's say that you have a wafer and you are going to develop the complete system, you are going to package the entire thing, and you want to do the complete system level characterization. That's also we can do it, right? So why do we need the wafer level characterization? Because as we know that more than 90 to 95% of the cost will go in packaging itself, right? Let us say that if your device, whatever the wafer you have developed, is not up to the mark and you have packaged it, right? Then you are in an utter loss, right? So you don't want to waste your 95% of your cost, isn't it? So that's why in the wafer level itself, you should be able to see whether my whatever is the fabricated device is up to my expectation or not, right? So the wafer level characterization plays a very, very important role. Once we see that the wafer level in the wafer level itself is up to the expectations, then only you please go forward for the system go forward for the packaging, and then for after the packaging, you can go forward for the system level characterization. For example, let us say that I wanted to develop a MEMS gyroscope under consideration. Then what would happen? Let's say that initially I will do the wafer level characterization, and in the wafer level characterization, I will go forward for the measuring the resonant frequencies, natural frequencies using the microsystem analyzer, and also I would like to figure out what are the electrical properties of the system for which I can make use of the electrical characterization or EVCV measurement unit, right? So one need to do all the electrical characterization, the mechanical characterization at the wafer level, and later on you take up the wafer and you take up the ASIC and you take up the wire bonds and you integrate the entire thing, and later on you can put it on the rate table and you do the entire system level characterization on it, right? So one can do the complete system level characterization and you can come out with the complete performance characteristics of your entire sensor. So this is what I already told you about that MEMS are intelligent systems and what does the MEMS basically consist of. So let me know, I will just skip this slide. So how can we fabricate these devices? The MEMS fabrication can be done by the micro machining process. So typically the size will be in few micrometers. So there can be several chemical and the physical processes are available. So microfabrication techniques are actually developed from the IC component. So IC fabrication indeed is the key, right? So what are the fundamentals? Because as the majority of you may already know about the IC fabrication, and also I will be taking up a separate session on the fabrication. So for the time being, I'll just skip this slide. So what are the fundamental difference between a microelectronics and a MEMS, right? If you take up the majority of the microelectronic structures, they are primarily two-dimensional structures, and they are just made out of a passive electronics under consideration. On the other hand, if you take up a MEMS-based devices, they are complex 3D structures. We do have a movable mechanical part associated with it. And unlike if you take up a microelectronics, they will transmit the electricity and then they do have the specific electrical functions. On the other hand, if you take up a MEMS devices under consideration, then what we need to have the variety of the biological, chemical, electromechanical, and optical functionality should be there associated with it. And then whenever you take up a microelectronics under consideration, usually they will be made out of silicon and silicon compounds. On the other hand, the MEMS-based devices, it is not just with silicon, even they can be made out with several polymers, quartz, gallium arsenide, several ceramics, metals. The plenty of materials you can use in case of MEMS. And also, as I told you, the MEMS is also made out of several movable mechanical components are there in the MEMS devices. The IC is already a matured one, whereas in the MEMS, there is a lack of engineering and the design methodology should be evolved in case of MEMS, right? And also it has a, this is the main thing, what you can see here, the packaging is already well established in case of microelectronics, whereas in case of MEMS, it is at the infant stage. And also the mass production is possible here. The batch production is also possible over here. And also it's primarily it involves what your electrical and chemical engineering, that's all. In case of microelectronics, on the other hand, it involves almost all disciplines in case of MEMS. Whether you are an electrical engineer, whether you are a chemical engineer, whether you are a mechanical engineer, whether you are a biologist, everybody can be involved in case of MEMS. The MEMS is completely interdisciplinary, right? Whether you are a physicist or you are a biologist or you are a mechanical engineer or you are a chemical engineer, everybody does has a way has the option to play in case of MEMS, right? So, for example, any of the electrochemical process, which is basically the electrical engineers do play a role. On the other hand, It is not just the electrical engineers, even the mechanical engineers, wherein they need to, we need to design the micro mechanics for this, right? And also we need to design the mechanical linkages and mechanisms associated with it. That is where even the mechanical engineers play a role. For example, even I told you that once we once we design any of the devices and fabricate it and we get the fabricated devices, after the fabrication, we need to package it. For the packaging, again, the packaging and assembly is again a mechanical property under consideration. That is where again the mechanical engineering do play a role. And also the materials persons play a very, very important role in MEMS, right? So there are several set of materials we can use it for MEMS. It is not just one material like your microelectronics, which is basically from the silicon-based family, whereas in case of MEMS, there are plenty of variety of materials are available, starting all the way from silicon, which is a abundant material that because sand is there from the sand, you can always sand to silicon, you can easily make it up. So it's just the fundamental one. Starting from silicon, you can even well go to a germanium, even the ZNO, and also soft elastomeric materials also for case of MEMS and MEMS. And also, these chemical engineers do play a role because whenever you take up any of the microfabrication process and thin film industry, then the chemical engineers play a very, very important role. Right? If you take up any form of engineering under consideration, this will indeed will fall into a category. They will have a role to play in maths. So when it doesn't matter whether you are an electrical engineer, mechanical engineer, chemical engineer, each and every person has a role to play in case of maths. So the summary of the first portion of my talk today is the miniaturization of the machines or the devices is an inevitable trend for the technology evolution. And then the MEMS technology will be further scaled down to the nano level. That's indeed what we call as a nanotechnology, right? That's what we told as a top-down and bottom-up approach. And then third one requires the application of the principles in the multiple disciplines, not just one discipline. It's a multidisciplinary approach in case of MEMS. We don't say that I am just a mechanical engineer, I only look into the mechanical. No, that's all. It's a completely interdisciplinary under consideration. It indeed requires a team effort for the team effort involving several engineering disciplines. Right. So it's a completely interdisciplinary. For example, all of you are using your smartphone, right? So if you look at the smartphone, you do have the touch screen. How does our touch screen basically work? Or touch screen basically, if you touch, you indeed get a feel, right? It is basically a capacitive sensing. Whenever you are going to touch, there is basically a deflection. So there is a deflection, that's indeed is a parallel plate capacitor. The capacitance of a capacitor is given by A epsilon by T, right? So if there is a change in the air gap, then there is a change in the capacitance, right? So because there is a change in the air gap over here, the D is changing. So there is a change in the capacitance. Or also if there is a change in the surface area of overlap, then also there could be a change in the capacitance. Or as we know that it's A epsilon naught divided by D. If there is a dielectric media between the two, if there is a change in the dielectric media, then also there could be a change in the capacitance. Yes, please. Any doubts? Shumit, any doubts, please? If you have anything, please do let me know. Any doubts? Anyone? Any doubts, please?
No, sir. Please continue.
Thanks, Carlos. Thanks, Carlos. Please. Let's go to Okay, now the another fundamental thing, whenever you are going to design any of the capacitive-based sensors under consideration, now let us say that I am going to design a capacitive-based sensor or a capacitive-based actuator. The first and the fundamental thing you need to understand is what is the, let's say that if I am going to apply a voltage, then what would be the electrostatic force under consideration, right? So let us say that I have the two parallel plates, right? So let us say that W is the overlap width, L is the overlap length, and G is the gap between the two parallel plate capacitors, right? If that is the case, we know that the energy stored in a capacitor is half CV square, correct? So where C is A epsilon naught divided by G. That's for a parallel plate capacitor, right? Now on the other hand, if you look at A is basically area of the overlap. This is area of the overlap is width of overlap and length of overlap, that is W into L divided by G and times V square, right? And if you take up the derivative of this energy along the respective direction, it will basically gives us the force, right? So force along the respective direction is basically given by the derivative of energy along the respective direction. So if you take up the derivative with respect to length, it will give basically the force in the length direction, and then the derivative along the width direction, we take it up, it will give us the force along the width direction. And similarly, if you take up the derivative along the gap direction, it will be, if you take up derivative with respect to gap, it will give you the force along the gap direction. If you look at the force along the width direction and the length direction, we can see that force along the length direction is independent of the length of overlap, but it is directly proportional to the width. On the other hand, if you take up the force along the width direction, it is directly proportional to the length of overlap and it is independent of width of overlap. On the other hand, if you take up, go to the third one, there's the gap direction. We see that it's you can see that it is inversely proportional to square of the gap. So if I'm going to take up gap G along this and the electrostatic force, then it is inversely proportional to G square. If I come down to, if I reduce the G value, what will happen? My electrostatic force will shoot up, right? So it will is proportional to 1 over G square. So whenever you are going to fabricate any of the devices, we need to go to the clean room and then we need to fabricate. These are some of the devices, what we have it at base. And indeed, we are even developing a full-fledged fabrication facility at the BITS Pilani. Next time, we can even, well, if any of you are at the North India or Europe, you can, next year, we may be able to fabricate the entire thing. Entire full-fledged fabrication will be there at BITS Pilani. You will be able to fabricate it. I think some of us, and next door for us is Siri Pilani. They also have a full-fledged fabrication facility with them. And these are the some of the facilities which are already there with BITS Pilani. That is the clean room which is there at BITS. And this is a class 100 clean room, class 1000 clean room. And next we will be switching on to, depending on the scaling. That scaling will basically tell us, now, till now, I basically now introduce you to what exactly is this technology all about. Now we will see, now majority of us have the feel of how the devices work at the macro scale, right? Now, let us say that now we are going to scale it go from macro scale to micro scale and see how does the different physical phenomena will further scale. So that is what is basically we call it as the scaling laws, right? So I already told you the basic motto for the miniaturization. So we know the cost per product will come down quite drastically. So and then this some of the micro scale devices, if we make it bigger, then they may not work. And then scaling down indeed will favor some of the micro scale devices, and then the cost per product will come down and the weight will be quite small at the micro scale. So the power consumption will also be less, right? And one can even will make use of the distributed arrays. For example, you can make, you might have seen the optical arrays, all those things. So you might have seen for majority of your LCDs, all those things. They indeed make use of the distributed array. A distributed array of micro mirrors under consideration. So, if I take up the scaling of the microsystems, there are several, because the microsystems, it is not just mechanical or electrical. So, indeed, we do come across the mechanical physics, thermal physics, indeed the electrostatics. What one can even will have the electromagnetic actuation as well. So let us see how does the magnetic ones will act, and what would happen with respect to the fluidics, and what would happen with the optical phenomena, and how about the biochemical assays, acoustics, power, and let's look into all of them in detail. So if I look at the basic scaling law, now look at this. This is my macro one, and let's say that L is the length. Let's say that this is 10, that is in the macro world, and 0.1 is the length in the micro world, right? Now look at this. This is the length. Now, what would happen to the area? Area basically scales as L square, right? The square of this is 100. Now, cube of this is basically the volume. Now, see that the volume is larger in case of this, right? The volume is much larger than the area, which is larger than this. This is the case of the macro, and this is the case of a micro. In case of a micro, look at this. If I take up the square of this will be 0.01. If I take up the cube of this, it will be 0.001, right? So you can see that the volume is much smaller than the length, smaller than the surface, it is smaller than the length. So if you take up the surface area to volume for this, naturally, since the surface area is larger than the volume, or since the volume is much smaller than the surface area, so surface area to volume ratio will further shoot up at the micro scale, right? So what does that mean? That basically means the surface effects will overtake the volumetric effects, Which are the volumetric effects that you can think of? For example, the self-weight, right? The self-weight is a volumetric effect. And then, what is the surface phenomena? For example, surface tension, correct? Surface tension is one of the surface phenomena. Can anyone tell me which are the other surface effects other than surface tension? Please tell me, please, which are the other surface forces which you can think of? If you want, you can type or you can speak. Capillary reaction, that's what I told you as the surface tension. Any other force, please? Any other thing other than the surface tension? What Schmidt said is correct, capillary action. Anything else, please? You can speak out, no issue. Yes, please, you can speak out. Okay. Pressure. Okay, Vinay is studying pressure. Okay, let's see. For example, one is that yes, Sumit has said capillary force, capillary action, it again boils down to a surface tension. For example, you take up an electrostatic force. Electrostatic force is what type of force? Is it a surface force or a volumetric force? In the previous slides, I showed you about electrostatic force, right? Is it a surface force or a volumetric force? Is it surface force or volumetric force? That's again the surface force, right? Now, look at this. In this, we have the Galileo bones. So what exactly is the Galileo bones? Here we have two of them. We have a smaller bones and we have a larger bone. Look at this. First, what I will do is that I will take up a small bone and now I am going to increase the length, right? I am going to increase the entire dimension. Now look at this, whose thickness has been multiplied until the corresponding larger. You might have seen the smaller animals and the larger animals. And if you look at the bones of the smaller animals and if you look at the bones of the larger animals, you know that the larger animals will have a larger bones and the smaller animals will have a smaller bones. Why is it so? Why is it so? Why the larger animals have a larger bones and smaller animals have a smaller bones? Yes, this is for a larger animal, right? Yes, means yes, to support the body weight, precisely, right? Because the larger animals have a larger body weight and so that they need larger bones. So why is it so? If they have a larger body weight, what happens? If they have larger body weight, then stresses induced on the bones will be quite large, right? So let us look into all of them. So why is it so? Why the smaller animals have the smaller bones and the larger animals have the larger? Now, on the other example, if you take up the different things, right? Take up the skeleton weight of the whales, then even well measure take up the skeleton, you measure its length, you measure its mass. You can take up the different body parts and measure its mass and measure its length and basically tabulate this, right? And if you look into this, they basically follow some allometry. You can take up the length along one axis and then you can take the mass along the other axis, wherein y to be a function of x, then if you plot it up, then it won't be, if it's isometric colorimetry, it will basically get a straight line whose slope is unity. That is basically what we call it as isometric scaling or isometric colorimetry. On the other hand, in general, whenever you take up any of this, if you plot it up, you don't get isometric colorimetry, rather it will come out to be a function of y to be equals to alpha times x to the power of beta. It will be indeed anisometric allometry under consideration. And also, you can take up the nails of different diameters. Depending upon the diameter, the length of the nail will also be different, right? You arrange the nails of larger dimensions to smaller dimension, and you measure the nail diameter and you measure the nail length, right? And these are basically the experimentally measured data points. These are what is there, the dots you can see here, right? You can see the dots here, right? These are experimentally measured data points. If you look at this, as I told you, this is basically a case of isometric colorimetry is what is Well, you may say that why not it could be isometric colorimetry? These are experimentally measured data points, right? And if you measure the slope of this, you can see that slope comes out to be 2 by 2. So whenever you take up any of the natural phenomena under consideration, majority of the natural phenomena, you don't get an isometric colorimetry under consideration. Rather, you would get an anisometric colorimetry, or you would always get an expression like y to be equals to alpha times x to the power of beta. So you do get several scaling, and also I told you about larger animals and smaller animals in the previous slide, right? Is the self weight really important at micro scale? Is it really important at self weight? Is self weight really important at micro scale? Can anybody tell me, is self weight important? Is self weight important at micro scale? Is self weight important at micro scale? Okay, and then because as I told you that whenever you look at the micro scale, the surface area to volume ratio will be very, very small. The volumetric effects are very, very less. So self weight is a volumetric effect. That's what I said. So can we neglect the self weight completely? If at all we are neglecting the self weight, then inertia basically comes from the weight, right? Weight of the object. So can we neglect the inertia also? Right? And also, right? Can we neglect the inertia? We need to see that as well, right? And the third one comes, you can use the electrostatic forces because, yes, please. These electrostatic forces are always attractive. Case the magnetic forces are really useful at the micro scale. We need to see each one of them. Let us see one by one. Let's start the question one by one. First one was, is the self weight really important? Now take up a first and the fundamental one. The first one, consider a fixed beam, right? Because of the self weight, I have basically written it like a uniformly distributed load, right? Whose basically is rho AG, right? That L is the length. Then the deflection is given by QL to the power of 4 divided by 384 L. And here is basically a micrometer to fix a fixed beam, right? And here, as we know that I is the moment of inertia, which is given by BH cube divided by 12. B is basically scaled as what? Alpha 1 times length is separate. And this H will basically the H cube I have. So I have L and I have L cube. So this is proportional to L into L cube. So it will be proportional to L to the power of 4. So that's what it is written here. Alpha 1, alpha 2 cube divided times L to the power of 4 divided by 12. So if I'm going to substitute that over here, so here Q into L to the power of 4 and I have L to the power of 4. So I basically get this equals to Q divided by E. Q is what? Rho AG. A will basically scale as L square. So you can see that delta is directly proportional to L square over here. So if I go to take up the relative deflection basically comes out as proportional to L. What does that mean? So which means to say that once I go from macro scale to micro scale, the relative deformation will come down, right? The relative deformation decreases once I go to once I go from macro scale to micro scale. And what would happen to the stresses? The stress is basically given by what? My by I, where m being the moment, So if I'm going to take up a beam with a distributed load, So if you take up any cross section across this at a distance x from here, so what do you get? Here I will get q times x acting at the center multiplied by x by 2. So this will be x is basically a length scale. So that's what I have written here. Q times L square is basically the length scale times y is basically p into L, and the moment of inertia is scaled as L to the power of 4. Here this is scaling as Q is basically rho Ag. So L is here L to the power of 4 will come. Here L will come. Here L to the power of 4 will go. L to the power of 4, L to the power of 4 will cancel out. Here we can see that sigma is directly proportional to the length. So what does that mean? Whenever you take up a larger animals will give us larger stresses. Stresses induced will be huge. So as to ensure that since the stresses induced are huge, that's why the large, so as to support those internal stresses which are induced on the animals in the larger animals. That's why the larger animals need have a larger force, and the smaller animals, because of the self weight, since the stress induced are less, they will always have the smaller ones. And these are also, I was mentioning that if the self weight is, since the self weight we are going to neglect it because of the self weight, since the deflection is very, very small, can we neglect the self weight? Because as we know that since stress is also directly proportional to L, and delta by L is also proportional to L. So both relative deformation and the stresses both are very, very small. Can we neglect the self weight completely? Right? So, is it so? Because if at all we are neglecting the self weight, the inertial sensors, right? Majority of the inertial sensors like accelerometers, gyroscope, even these micro machine gears and gear price, then how can these inertial forces are really less at the micro scale? Whenever you take up a micro, yes. If you don't have any questions, can you please mute? If you come to a micro scale, with again in that case, if you take up any of the inertial sensors under consideration, how does the inertial force basically will scale? Inertial force will basically scale as m omega square times x, right? Even though the mass is very, very small, what happens to the frequency of operation of this sensor, of this micro scale structures? So usually these microscale structures, the frequency of operations are huge in contrast to the macro counterparts. That is why these inertial forces are quite significant at microscale. One can't neglect the inertial forces. So you can look at this, take up a simple cantilever, and if you look at the expression for the natural frequency, you can get to see that natural frequency is inversely proportional to the length. So, which means to say that, so the frequency of operation will shoot up once I go from macro scale to micro scale, right? So here these are basically the micro machined beams. You can see that the natural frequency of these beams are indeed in the range of few megahertz, right? Few megahertz. So getting the frequencies in few megahertz are quite regular once it comes out to the micro scale. Now, on the other hand, if you take up the same thing, the macro counterparts, they will be typically in the macro counterparts will be sometimes will be in few hertz, and at max they will go to few kilohertz. They won't go beyond that. And sometimes, when in the majority of the times, whenever you are going to go by the surface micro machining, and after your fabrication, you are going to do the micro machining. You are go after once your design is done, you are going to do the fabrication, right? So whenever you do the fabrication, you can see that sometimes your structures will either curl up or it will curl down. It will, what would happen? Because whenever you do the fabrication, you are going to deposit, and then you are going to remove the deposited layers. Doing the process, you are indeed will take it to the thermal cycling process. Whenever you go, it will undergoes to thermal cycling, the stresses gets induced within the structure. So this is like unwanted residue which will induce unwanted residue, unwanted residue which comes out from the fabrication. These are the stresses which are the unwanted residues which comes out from the fabrication. That is why we call it as a residual stresses. That's the residue which is coming out from the fabrication. These are the unwanted, these are the residues are nothing but the stresses induced in the structure. That's why we call it as residual stresses, right? So these residual stresses, sometimes they are useful, sometimes they are deteriorating the performance. For example, these residual stresses indeed will change the natural frequencies because these residual stresses indeed will modulate the stiffness of the structure, right? So also sometimes they are all indeed helpful as well. For example, whenever you want to develop a new set of sensors for a novel sensor, for example, like for the virus detection and other things for which, let us say that if you have the curved beams under consideration, they indeed will improve the performance of your sensor under consideration. So if at all you want to realize the curved beams, then is always the curling will basically comes up from your residual stresses. So these residual stresses sometimes will be used. And also I was talking to with respect to the forces, right? So this is basically a micro-machine Coombe drive actuator. So what exactly does the Coombe drive actuator basically consist of? The Coombe drive actuator basically consists of a shuttle mass suspended with the help of set of beams, and we have movable set of Coombe fingers which are attached to the shuttle mass, and we have a fixed set of Coombe fingers attached to the proof mass. These are movable set of Coombe fingers attached to this, and here I have fixed set of Coombe fingers attached to the substrate. So here I am going to show you this. These are basically the images of this, and here I am going to show the see this. This is the shuttle mass what I have. This is a mass, and here basically a suspension. This is a suspension over here, and this is suspension is fixed onto the substrate over here. And here I have a movable set of Coombe fingers, and these are the fixed set of Coombe fingers which are anchored onto the substrate. Now I am going to apply a potential between a fixed set of Coombe finger and a movable set of Coombe finger, and let's see what happens. Let's see if I am going to apply a potential V across the movable set of Coombe fingers and a fixed set of Coombe fingers, then there is an electrostatic force, correct? So whenever there is an electrostatic force, this electrostatic force, as we have already discussed in the earlier slide, that electrostatic force is directly proportional to V square. That basically comes from the energy. From the energy, you can obtain the force. Right? So one can get the electrostatic force, and then stiffness. Basically, since the guided cantilever under consideration, here we have two of them. Note that we have one suspension which is coming here, another suspension on this side. We have two of them. So it will basically comes like 2 times ETW cube divided by L cube, two guided cantilevers for this. On the other hand, this is basically electrostatic force, and then the deflection is basically force divided by the stiffness will basically gives me the deflection. So I am taking this, dividing it by the stiffness, that will gives me the deflection of this. So if you look at the deflection, it basically scales as n epsilon naught v squared divided by this. If at all you want to look at the relative deflection, that is delta divided by L, see how does it scale? It basically scales as n epsilon naught v squared divided by 4e. This is the term I am retaining as it is. This is L square, L to the power L cube, L1 has gone here. This is L square divided by GW cube. Now look at this. Here I have L square term. Here I have L to the power of 4 term. Because W also is proportional to L. G is basically the gap. Gap is also proportional to L. So I have L to the power of 4 in the denominator, L square in the numerator. So it is inversely proportional to L square. So you can see that delta by L is proportional to 1 over L square. What does that mean? So that means to say that the relative deformation for a fixed voltage, as long as the applied voltage remains the same, the relative deformation at the micro scale will be much larger than that at the macro scale. For example, you take up a macro scale object, you require a huge potentials to actuate them, right? On the other hand, to come to a micro scale object, you would require, even at a much smaller potentials, you can actuate them, right? That's what this basically says, right? The relative deformation would be much larger at the microscale at the fixed voltage. Now, take up the same expression now, take up the same relative deflection expression. Now I am going to rearrange this term to get the voltage one, right? Now that basically I am rearranging this to get the voltage. So we can do the dimensional analysis for this. Here I have L to the power of 4 in the numerator, L square in the denominator, underneath the root. So it is square root of L square, which is nothing but L. So we can see that the applied voltage is directly proportional to the length. What does that mean? The scaling of the voltage for the fixed relative deformation. For the same relative deformation, we would require much lower potentials for the micro scale structure in contrast to the macro counterparts, isn't it? I think this would make your things clear. So whenever you want to use it in actuator applications, your microscale structures will require much lower potentials in contrast to macro counterparts. Now coming to the magnetic action, I hope the electrostatic actuation is clear. Now coming to the magnetic actuation. Now let's take up a two electromagnets. So let's see that I is the current, I1 is the I1 and I2 are the current flowing through this. Then the force is basically given by this, right? Now let's assume that the current density is the same. Then current density is basically I divided by A. Then we can say that what, as long as current density remains the same, then if this is a constant quantity, then I will be proportional to A, which is nothing but L square. If I go to substitute over here, then you basically get force to be proportional to L to the power of 4. You can see that once I come to a micro scale, force is very, very bad. The magnetic force of scale is extremely bad. On the other hand, if there is a temperature rise also, we can see that the force is proportional to L square. That's also very, very bad. But still, with a powerful magnet, one can even well develop the electromagnetic actuation at the micro scale, right? Now, if you want, I can even well show you. There are papers from Professor Suresh also, wherein he has developed the electromagnetic actuators at the micro scale as well. Even Alan also, there are plenty of papers on that. I can share it with you. Because just as a matter of time, I will just have another 10 to 20 minutes with me so that I can take up the questions also from your side. Now, on the other hand, look at the temperatures, right? Why do you might have seen that elephants usually have the larger ears and dinosaurs, we do have the fins. Whales have the fins, right? Why is it so? Why is it so? Why elephants have larger ears and dinosaurs fins? Yes, please. Any take? Why do elephants have larger ears and dinosaurs fins? Why is it so? Okay. Yes. Yes, please. Why is it so? Yeah. Elephants, yes, workers, radiators. Okay. Schmidt says control the heat. Okay. Okay. Good. Now, if you look into this, right? Note that metabolic rate basically scales as body mass to the power of 3 by 4. Body mass to the power of 3 by 4. If you take up elephants, the body mass is huge, right? Since the body mass is huge, the metabolic rate is also huge. And also similarly that of a dinosaurs. Dinosaurs' mass is also huge. That's why their metabolic rate is also huge. If the metabolic rate is huge, then the amount of heat produced will also be huge. Why is it so? Because if you look into this, the temperature rise due to the metabolic process is basically given by delta T equals power multiplied by RTH, where RTH being the thermal resistance, right? Where thermal resistance. Note that the power we can retain as it is. Now the thermal resistance basically scales as 1 over HA, where H being your heat transfer coefficient. Now, if P is the power, right? Now you consider small p to be specific power multiplied by the volume is the power. HA I will retain as it is. Note that V is the volume and A is the area. Volume divided by area basically scales as length, right? So this is L cube divided by L square. So it is basically scales as L. Note that the temperature rise is directly proportional to the length, right? It's directly proportional to the length. And also the metabolic rate is directly proportional to the body mass to the power 3 by 4 as per the Kepler's allotropic relation. I told you about the allotropic relations earlier, that is y to be equals to y some alpha times x to the power of beta, right? So here the beta is basically y3 to the power of 4 with respect to the metabolic rate and body mass. Now, note that your heat transfer coefficient also scales non-linearly with respect to this. Now, you see that both elephants and dinosaurs will get heated up. So as to release the amount of heat which gets induced within the body, they have to relieve that heat somehow, right? Now, usually whenever you take up the engines, on the engine surface, we do keep the fins, right? Because why do we keep the fins? Because these fins will radiate out the heat quite easily. Because we do get, on the other hand, for the elephants, we do get a larger surface area for convection. This convection, because these elephants will radiate the heat by the convection process. Because the convection, they can easily relieve the heat which is induced from the metabolic process. That's why the elephants usually will have a larger ear and the dinosaurs will have the fins. Now, coming to your microfluidics, now note that whenever you take up any of the fluidic phenomena, how does the Reynolds number basically will scale? The Reynolds number is basically a ratio of viscous force, ratio of inertia forces to the viscous force, right? So inertia force is basically depends upon what is the mass, right? So rho Vd by u or rho Vl by u is what we write. So where u being your velocity, which is basically meters per second, which is proportional to the length scale. That's what it is written there. And L. So you can see that Reynolds number is proportional to L square. What does that mean? Once I go from macro scale to micro scale, once I go to the micro scale, the Reynolds number reduces quite drastically. That's why mixing is quite difficult at the micro scale. That's why you can see that small insects rather swim, right? Small insects swim in air rather than they are flying. Now, what would happen to the diffusion? So if you take up the diffusion coefficient, it will basically scale as kT divided by 6 pi eta r, where K is the Boltzmann constant and T is the temperature, and eta being the viscosity and R is the hydrodynamic radius. And here you note that the diffusion coefficient D to be equals to if T is the time. For the diffusion distance X, note that if D is the diffusion this, you note that now for the from this you will take up this expression. Look at this for the as long as the diffusion coefficient remains the same. So now the time taken for the, let's say, 10 micrometer will be much million times faster than that for 10 millimeters, right? As you can understand it quite easily from this expression, because X is directly proportional to, because there we have the hydrodynamic radius down over here, right? Because the D will be inversely proportional to this 1 over L. So that's why it will usually take up much because that diffusion will be much faster on the micro scale in comparison to this. On the other hand, if you want to go to a macro scale object, we need to make use of pumps and tubes for the macro sized object. Without having the pumps and tubes, you can't do for the mixing at the macro scale. On the other hand, since the diffusion is quite good, in the previous slide I said since the Reynolds number is very less at the micro scale, the mixing is difficult. But look at this, the diffusion, it favors at the micro scale. That is why, because since the diffusion is good, that's why mixing is much easier at the micro scale. Now coming to the Knudsen number also, we can basically means we part the characteristic line. So note that whenever you take up the Knudsen numbers, depending upon the value of Knudsen number, one can categorize it into slip flow, non-slip flow, and the MD regime. And you can, as I told you earlier, that surface area or surface effects will overtake the volumetric effect. So surface tension plays a very important role once you come down to the micro scale. So that's why we can see that insects indeed walk on the water surface, right? So how does the take up two capillaries, one with a larger diameter, other one with a smaller diameter? If the diameter is small, that means what your bond number basically scales as the gravitational force to the surface tension forces. Okay, this is basically a gravity force. This is a surface tension force, right? Note that if the diameters are very small, then what? This is a small bond number. If the diameters are large, then this is a larger bond number. If the diameters are large, then we can see that for the smaller bond number, what does bond number is small means? My surface tension is large, right? The surface tension is large, then it can easily the rise in the capillary. On the other hand, if the smaller bond number means there is a larger, smaller bond number is larger bond number means the surface tension is very small, then there is a dip in the capillary, right? So that's why we can see that whenever the capillary tube diameter is quite large, that's a larger bond number, then there will be a dip in the capillary. On the other hand, there will be a rise in the capillary with respect to that. And then with respect to microfluidics, we can actually play with the fluids in the micro scale, right? One can make up the several channels. One can make up the several channels, and you can even well play with the fluids at the micro scale. And this is what is basically zoomed it over here. This is a junction over there, and within that junction, either you can transport the fluid. Either you can transport the fluid from one to other, or you can merge the two fluids. You can cut the two fluids, or you can cut one fluid into two. You can cut the fluid, you can merge the fluid, you can transport the fluid, or you can even well go to EWOD platform, which is basically electrowetting on dielectric. So here I have a bottom substrate on top of which I have an electrode. This is basically my electrode layer. Now, take up that I have one bottom substrate, I have an electrode. Now let us say that I will directly place a fluid on top of this, right? Now what would happen if I am going to apply a potential between fluid and this? What would happen to this? It will, what would happen if I apply a potential directly between fluid and the electrode? Why do we require a dielectric? Why do we need a dielectric? Yeah, sure. I am winding it up. Because if I don't have a dielectric layer between the two, then you will get a short circuit between the two, right? That's why we need a dielectric layer between the two. That's why this is also called electrowetting on the dielectric. So whenever you are going to probe it, you can see that there will be a change in the contact angle between the two. So if I'm going for which I need to go into the fluid, I need to measure the contact angle, and it's a completely reversible process. So this basically entire area is what we even call the digital microfluidics. So one can even well play with the optics also. The wavelength of light indeed falls within this. So one can play with the light, and one can even well play with the acoustics as well. So there are plenty of things we can do with MEMS, and one can do with the several combinatorial assays. Okay, everything again boils down to this, and whenever you are implementing it in a software program, you multiply your input by 10 to the power of 6 into A, and then you multiply the output with 10 to the power of minus 6 to the power A. And that's what we even call it as micro MKS units. We do have MKS units. One can even will go to micro MKS units and then go. So these are the typical scale factors, what you get out for different quantities. So I will stop here. If you have any doubts, I will be ready to take it. Thank you very much. Yes, any doubts, anything?
Thank you, Professor Venkatesh, for the talk. The webinar will be available after the session. I will upload on the video and we'll let you know the link in order to view the link if it was not possible today, and if you want to review it later. But now you have the opportunity to ask some questions to Professor Venkatesh. In case not, you have his email, and if you have any question about the training sessions, you have also the emails of Veda and mine. You can write to us. I just want to remind you that the next training will be on November the 1st. In this case, the time will be different, between 7 and 9 Indian time. So, yeah. There are no questions, so I would like to ask everyone, we have a few minutes, to please switch on your video just to see all of you, all the attendees at the session, please. Everyone. Hi. So it's been a pleasure to be here today with all of you, and thank you again to Professor Venkatesh for the talk. I hope you enjoyed the training, the webinar today, and I hope you can follow the next sessions. In case not, please write me an email. We can coordinate with different chapters in case you can join other sessions, and otherwise you will be able to follow the recorded sessions online. So I have nothing to add. In case you have something to say, Professor Venkatesh, or anyone has any question.
Yes, if you have anything, you can either ask right away, or you can even write to us anytime.
Okay, so thank you, everyone. Have a nice morning, evening, or see you.
Yeah. See you all.
Yeah, bye.